Okay, now let's move past hydrogen. We already know we can't compute exactly anything more than a two-body problem, so we won't be able to use the new physics to compute exact energies of atoms bigger than hydrogen. But the quantum mechanics also came with some rather straightforward methods to approximate the other atoms, using the hydrogen orbitals as a guide.
So what modifications can we expect for multi-electron atoms? Well, the major difference is that there are subtle changes in the energies of the quantum levels of these atoms when compared to hydrogen energy levels. Notice the new energy structure for the different orbitals in the diagram. As before, for each principal quantum number n, the p orbitals have higher energies than the s orbitals, d orbitals have higher energies than the p orbitals, and the f orbitals are above the d orbitals as expected. But here's what is different in the new energy structure of orbitals. The layering of the energies is such that the 4s orbital is lower in energy than the 3d, the 5s is below the 4d, and so forth. This is a very measurable difference when compared to the hydrogen atom's energy levels, which have the same energy if they have the same principal quantum number. Now, a cool way to remember this ordering of the energy levels is demonstrated in the following diagram. Now, if you follow the arrows, you see that the ordering matches the arrangement of the energy levels in the other diagram. Now, when filling the orbitals with electrons, we fill the orbitals with the electrons starting from the lowest energy orbitals to the highest in order of increasing energy. This is called the Aufbau Principle. Now, we do this while also obeying the Pauli Principle, which tells us to fill each orbital with a maximum of 2 electrons. Now, what happens when we have several electrons left and several orbitals having the same energy, such as 4 electrons going into 3 p orbitals having the same principal quantum number? Well, a pattern was noticed by the scientist Frederick Hund when he was identifying the low-energy ground state electron arrangement of atoms. He saw that if we need to put electrons into a set of orbitals with the same n and l quantum numbers, we should first fill each of the orbitals with 1 electron before having to pair up the electrons. This observation is called Hund's rule. So, let's demonstrate how to use these 3 rules, the Aufbau Principle, the Pauli Principle, and Hund's rule, and see how they work together to produce the correct electronic structure of some atom. Now, we usually just say that these 3 rules are the normal buildup rules. Now, let's say we have an atom with 8 electrons. We first would place 2 electrons into the low-lying 1s orbital, one with spin up and one with spin down, then the next 2 electrons into the 2s orbital. Now we have 4 electrons left, which we want to place into the 3 2p orbitals. We apply Hund's rule when placing the remaining electrons into these 2p orbitals. Notice carefully how the spins are represented in this diagram. We will fill the 3 orbitals by half filling each orbital with spin-up electrons, and once we cycle through, we fill up an orbital with 2 electrons. Now, in a kind of shorthand, this filling of the orbitals with 8 electrons would be written as a 1s2, 2s2, 2p4. This filling of orbitals is called an electron configuration. Now, a neutral ground state oxygen atom has 8 electrons and would have this low energy ground state electron configuration. Now, you can memorize the diagram on the previous slide and generate ground state electron configurations for any atom, but there is an easier method that doesn't take as much memorization power. We can use the periodic table as our guide, and you'll always have a periodic table. The shape of the table begins to make a great amount of sense when relating electronic structure and different blocked regions within the table. The first 2 columns of elements of the table represent the s block of orbitals, where 2 electrons fill up a single s orbital. The 6p block set of elements are on the right side of the periodic table. There are 3 p orbitals that can hold 6 electrons to match up with these 6 elements. The middle 10 elements are the d block of elements, which makes sense because we know that there are 5 d orbitals that can hold 10 electrons in total. The actinide and lanthanide elements are the f block elements, consisting of 14 elements in the period. The reason? There are 7 f orbits which can hold a maximum of 14 electrons. So let's look at using the periodic table to generate the electron configuration for the neutral ground state of the element sulfur. Neutral sulfur has 16 electrons, which we get knowing its atomic number. Now, we'll use the periodic table starting at hydrogen and begin placing electrons in orbits according to the principal quantum number and block until we get to the location of sulfur on the periodic table. So let's begin. We're going to start at the top of the periodic table and place the first 2 electrons into the 1s orbital. The next 2 go into the 2s orbital. Continuing across to the p block, we then begin filling the 2 p orbitals with 6 electrons. Now we cycle back to the left and go down 1 period to the 3s orbitals and fill those with 2 electrons. Now we cross over to the p block and put the last 4 electrons into the 3p orbital, stopping when we get to sulfur within this 3p block of elements. The complete electron configuration is 1s2, 2s2, 2p6, 3s2, 3p4 for ground state sulfur. To check if this is correct, we could use the energy diagrams on the previous slide to generate the same electronic configuration. Go ahead and give that a try. Now at this point, you might be thinking about the tedious process of writing down complete electron configurations for higher atomic numbered elements like lead, which has 82 electrons. What a chore. So to get around this, we've come up with a different way of writing the electron configurations that is much easier to represent the atoms. We can rewrite the electron configuration for sulfur in a kind of shorthand. Neon, 3s2, 3p4, where the core and lowest energy electrons are represented by the bracketed neon atom. The 1s2, 2s2, 2p6 part of the electron configuration of sulfur is the same as the complete electron configuration for neon, the last noble gas we passed as we were building our electron configuration for sulfur. The last 6 electrons in the shorthand version of the electron configuration for sulfur after the bracketed neon are said to be the valence electrons for sulfur. And these valence electrons, we know, are where all the action happens chemically for this particular atom. So the valence electrons can be redefined in our new model of the atom as all the outer electrons in the electron configuration past the last noble gas configuration. Let's do another element, okay? Neutral cadmium has 48 electrons. Again, it would be rather tedious at this point to write the full electron configuration. So we simplify our work by writing down the nearest noble gas that has fewer electrons than our cadmium atom, which in this case is krypton, Kr. After that, we put 2 electrons in the 5s orbital and then move into the 4d orbital block where we put in 10 electrons. So the ground state electron configuration for cadmium would be written as Kr 5s2 4d10. The last 12 electrons for cadmium are then the valence electrons of this atom. Shown here in this slide is a complete list of electron configurations for the naturally occurring elements. As practice creating electron configurations, just pick an element from the periodic table and see if you can verify its ground state electronic configuration using our normal build-up rules. Hey, did you find some elements that didn't have electron configurations that you would have expected? Yeah. Some of the elements, most being located in the transition metals and actinide-lanthanide series, can have electron configurations that don't follow the normal buildup rules. Now here's a list of the elements with their ground state electron configurations that are exceptions to our regular buildup rules. One of the classic examples is that of the element chromium. Following our standard buildup rules, we would think that chromium would have the electron configuration of argon 4s2 3d4, but it actually has the configuration of argon 4s1 3d5. If we look closely at this configuration, we notice that the valence s and d orbitals are each half-filled. Sometimes half-filling the orbitals can minimize the negative charged electron repulsion between the electrons, thus lowering the overall energy of the atom. Such is the case for chromium. Molybdenum, MO, found right under chromium in the group, also follows this exception, having an electron configuration of half-filled 5s and 4d orbitals. But the element tungsten, W, also in this group of elements, plays nice and follows the regular buildup rules. Another well-known set of elements that don't obey the normal buildup rules are referred to as the currency group of transition metal elements, copper, silver, and gold. For copper, following our regular buildup rules, we would expect an electron configuration of argon 4s2 3d9, but it has the configuration of argon 4s1 3d10, preferring to fill the d orbital rather than the outer s orbital. The other currency elements, silver and gold, also follow suit. Speaking of the silver atom, let's look at that electron configuration again. Krypton 5s1 4d10. Hey, remember? This was the first atom used in the Stern-Gerlach experiment we talked about in previous lectures. It turns out that the lone valence 5s electron in this atom can either be spin up or spin down, effectively giving us the possibility of two different silver atoms. This now explains the experimental result, where two different spots were observed as silver atoms went through the magnetic field and collided with the detector.
We now have a clear picture and more knowledge about the electronic configuration of atoms. We've come a long way from Dalton's atomic law. We now know that the structure of the periodic table and the reactivity of the bulk elements has its origins in the electronic configurations and the valence electrons of the atoms that make up those elements. Folks, we've only scratched the surface of what we can do with this knowledge. Well, have a terrific day or night or whatever. I'll catch you later.